let's move on. So what is stereochemistry? Have you ever heard the word stereochemistry? For your A-levels also, you have learned some, not that deep, but just surface through stereochemistry. Actually, in Sinhala, it is Trimana Rasayana, right? And it is the study of the relative spatial arrangement, arrangement in space of atoms and groups of molecules. So in other words, we are going to study the 3D arrangement of the molecules and their manipulation. Manipulation is handling of them. And it is an important area of stereochemistry. An important area of stereochemistry is the study of chiral molecules. We'll discuss what chiral molecules are. And the study of stereochemistry is not limited to organic chemistry. It is also important in inorganic, biological, physical, and supramolecular chemistry, etc. Right? So it's not just limited to organic chemistry. So we'll start our discussion with a story on this thalidomide disaster. So everybody likes to hear stories. So let's see what it is. Now, this is a molecule which is called thalidomide, right? Not thalidomide, thalidomide. The compound name is thalidomide. It's a complex molecule. Don't worry remembering the structure of this one, just to show you what thalidomide is, right? Now, this was first, this compound was first marketed in Germany in 1957 as a drug for morning sickness in pregnant women, right? And later they found this compound, this drug to be teratogenic. That is, teratogenic means causing malformation of the embryo or the babies, right? So, this picture shows what happens when the compound affects badly on the human babies, right? And the chemists were thinking what has gone wrong, because it was working earlier as a sedative very well, and later this was giving problems. And after their search, their chemical research, they have found that there are two forms of thalidomide, and one is, as you can see here, one is R-thalidomide and the other one is S-thalidomide, right? So this R1 is the good one, R-thalidomide is the good one, which acts as a sedative, and this S-thalidomide is the bad one, right? So you can see what is the difference between the two molecules. They are both thalidomide, but at one point, you can see a difference. Here you have a hydrogen attached to this carbon atom. According to my drawing, it is away from the paper, right? This dotted line means it is away from the paper. And in the S-thalidomide, it is pointing towards you, right? Well, pointing towards yourself, right? So I have two pictures of the molecules, stick and ball models, but the difference you can't see here. Here it is going inside and it is pointing towards you, right? So you can see the importance. Now we can say the stereochemistry of this carbon atom is different in two molecules, right? So that caused the trouble, right? So it's, when you do all the testing, it is going to be thalidomide, but when the stereochemistry is different, it is going to cause disasters, right? So you can see the importance of stereochemistry, learning stereochemistry and the application side of it to some extent now, right? So there are several types of stereoisomers, right? So according to my chart, you can see according to my chart, I have shown you how they are divided. So isomers, you know what an isomer is. Look at my definition. Isomers have the same molecular formula, but different structural formula. Different structural formula, right? So commonly, isomers are those which are having the same molecular formula, but different structural formulas, right? So those isomers can be divided into two groups, like constitutional isomers and stereoisomers, right? Now, constitutional isomers, you know now, you know very well, may not be by the name. This is also called structural isomers. At A level, you have learned about it, right? So, the feature in those, the common feature in those constitutional isomers is same molecular formula, but different connectivity. The atoms are bonded differently. Maybe if you have a ON oxygen atom, it can be present there as an OH group or a ether group or something else, right? And stereoisomers are the compounds or isomers which have the same connectivity but different spatial array. The connectivity with carbon and other atoms are bonded the similar way, but in the space they are arranged in a different way, like this RNS thalidomide, right? So under stereoisomers, now we are not much interested in studying constitutional isomers because you have done a study at A levels, but our course material is covering those types of stereoisomers, where you have geometrical isomers, configurational isomers, and conformational isomers. Let's see what they are, what each of these things are, right? Conformational isomers. Am I recording this day school? Yeah, I think so. So, can you see that icon recording?
Yes, madam.
Okay, okay. So this computer is not much familiar to me, this CRC one. I have some problems, issues with that. So let's see what conformational isomers are. They are having carbon-carbon single bond. All the bonds in those molecules are carbon-carbon. All the carbon chain is having all the bonds as single bonds. And you know, when you have a carbon-carbon single bond, it can rotate freely along the axis of the carbon-carbon bond. So some molecules of this type can be interconverted. The bond can rotate at room temperature, giving different spatial arrangements, right? So then what are configurational isomers? They are isomers, maybe they have single bonds, but they are not interconvertible at room temperature, right? And the third type is geometrical isomers. They are also called cis-trans or EZ isomers. They have carbon-carbon double bonds, and you know, when there are double bonds, they have restricted bond rotation along the axis. And these configurational isomers can be further divided into two groups: diastereomers or diastereoisomers and enantiomers. Enantiomers are molecules which are mirror images of each other. And those which are not falling into this category, enantiomers, are grouped into this diastereomer isomer group. Okay, so just to recall on what you have learned at A level, let's see what constitutional or structural isomers are. As I mentioned, we are not going to study in detail about these constitutional isomers, just to get a clear idea what they are only. I have included these two slides. What are the constitutional isomers? As I mentioned, they are the molecules having the same molecular formula and different connectivity of atoms in space. Atoms, right? Actually, they have different groups, right? So that the structure of the isomers are different. They have different groups, right? I have an activity here. So hope now I always announce when you are joining my day's course, you need to have a pencil and a paper with you to work out the exercises, do the exercises, right? So I will give you a few minutes. My question is, draw all possible structural isomers or constitutional isomers for the following molecular formula. Okay, I think I have given enough time. Let's check. Check what you have got. Now you can draw. Now our compound has 4 carbons, 10 hydrogens, and oxygen, right? So you can draw several alcohols, structures of alcohols for that, like this. Right? Check whether you have drawn all 4. Right? You can have this OH group. You can write a linear structure like this or branch structures. And in this molecule, in the second one, or then the first one, you have this OH group at a terminal carbon atom. And the OH group in this molecule is in the middle. And then you have a branch CH3 group in this molecule. And here in the fourth one, you have 2 branches, right? Branch CH2 and as to the same carbon, OH is attached. And then you can write the structures of ethers, right? So one type of ether will be where you are having a C2H7 group, C3H7 group and a CH3 group, and the other ether can have 2 ethyl groups attached. So when you draw the structures, you will get this like this. Now here, the C3H7 part can be a linear one like this or a branch one like this. And when you have 2 ethyl groups, the structure looks like this, right? So hope you have drawn all 4, 5, 6, 7 structures for the molecular formula. So you can see these are all with the same molecular formula but different structures, and we call them structural isomers or constitutional isomers. So you have to get familiar with the word constitutional isomers and structural isomers. Both are the same, both refers to the same thing, and you get different structures. But remember, the molecular formula is the same. Okay, so under stereochemistry, what are we going to learn? So the book covers the study of conformational isomers and nomenclature of isomers. When you have the different types of isomers, there should be a way of identifying. So for example, if you just say thalidomide, we don't know what thalidomide, whether it is the bad one or the good one. So there should be a way of naming the molecule in a proper standard manner so that anybody can identify what type of the stereochemistry of that compound. So there are different notations to identify or name the things. There's one called cis-trans and EZ system for geometrical isomers. You are familiar with this type. And there's the other type, which is called RS system of nomenclature, and that is for enantiomers. Enantiomers are the mirror images of compounds. And then you learn tetrahedral stereocenter. You learn what a tetrahedral stereocenter is. Or first you learn what a stereocenter, and then you identify the tetrahedral stereocenters. And we talk about chiral molecules also. We learn the word what chiral is, and then talk about chiral molecules. Then you have to learn how to draw Kirchhoff projection formula, that is to show configuration of chiral molecules, and then DL convention of designation, and all these are in the book. Sometimes some of these I might not discuss at my DA school, but in the book it is simply given there. You can read and understand. So then we learn about optical activity, and we learn what a racemic mixture is and how to resolve a racemic mixture. And then we learn how to find out optical purity of a sample and how to calculate enantiomeric excess. And then finally, we learn about the molecules with several stereocenters. Under that, mesoisomers, cyclic molecules, and conformational enantiomorphism. And finally, we can talk about chiral molecules without tetrahedral stereocenters. And those are coming under the categories allenes and biphenyls. Okay, So what are stereoisomers? Now I have given you a broad picture by giving that the chart, the types of stereoisomers. So if you can remember now, they are the molecules having the same molecular formula and the same sequence of bonded atoms. Constitution is the same. In constitutional or structural isomers, constitution is different. But in stereoisomers, the bonding is the same. Sequence of bonding of atoms is the same. But the three-dimensional arrangement in space is different. The arrangement of atoms in space is different. Remember this talidomide, right? The hydrogen is one is pointing, the other one is pointing away, right? So 3D arrangement is different, right? So this is again to show you the types of stereo and the isomers we are going to study. We'll start with conformational isomers, where you have carbon-carbon single bonds, right? And then we'll talk about configurational isomers. Then next we'll discuss about geometrical isomerism, and then finally constitutional isomers. Okay. Now, as I said, these molecules are, look at this one. This is the structure of ethane, CH3, and carbon single bond is there, and you have another 3 hydrogens attached to the other carbon, and this is ethane. So it can rotate, as I said, this single bond can rotate its axis, giving rise to conformations, right? So if you look at my So look at this small video. You can see these gray balls are carbons and yellow ones are hydrogens. So due to the free rotation, it can give rise to different structural structures. So the position of hydrogens is different because of this rotation. Can you see? In one instance, one hydrogen is behind the other hydrogen. And in another instance, hydrogen is in between two other hydrogens of the next carbon atom, right? So I think it's enough. Let's stop it here. So if you represent the positions on paper, you can draw them like this. As I said, one is called staggered conformation. Staggered is the hydrogen is in between consider the back hydrogen, or if you consider the back hydrogen, the other hydrogen in front of you is at an angle, right? And it can be 60 degrees or maybe even different in between 1 and 60. Yes, because the angle between this one is 109, right? So it is called the staggered conformation. The other one is eclipse conformation, where 2 hydrogens are like this, right behind the other one, right? So it is called eclipse. So there's no bond angle here. The dihedral angle is 0, right? So in between, you can have different arrangements in between this 60 and this one. So let's again have a look. This is a stick and mod model, which is showing the single bond also. The earlier one you didn't see. I'm having a noise. Sorry about the noise. Okay. Hope you saw. Okay, now you can see, now you saw the conformational isomers and how they are changing due to rotation, and different conformations which it is acquiring when it is rotating. Now let's see how to draw structures for butane. Earlier, what we saw is for ethane, where you have 2 CH3s. But in butane, you have 4 carbon atoms. So when you draw the Newman projection, you hope you know the word, what the Newman, and this is the Newman projection of the molecule butane. You can draw like this. You have 1 carbon atom, and to that carbon atom, you have a CH3 group attached, and the other atoms are hydrogen. And behind this carbon atom, which is circled here, you have another carbon atom, and it is again having a CH3 group and 2 hydrogens, right? So when you rotate it by 60 degrees, you will get these structures D, right? And again, when you keep on rotating at 60 degrees angles, you get these several structures like this. Now you can see that in each position, you have different arrangement. In this case, you have CH3 and CH3, the 2 CH3 groups far apart, both this one, right? So here it is at an angle, and here the CH3 group is very closer to each other. And in the F structure, you have the CH3s one behind the others. Like that, you have different arrangements, and we call them different conformations, right? So when you draw the, okay, I missed one. Good. Sorry, I have missed one video. The problem is this computer, I'm getting noises. Just watch this. Note that it is regarding ethane, CH3. Now you can see, if you draw an energy diagram, you can see for ethane, you get a graph like this, where you have a high energy positions and a low energy positions, right? So high energy positions are where you have these two hydrogen, one behind the other. And when they are at an angle, you get the lower energy. And you get this same high energy and same lower energy because the two carbons have the same hydrogens, the same number of hydrogens attached, no other different groups attached to this one, right? So when you talk about butane, now I was before the video, I was discussing about butane. So in butane, one hydrogen is replaced by CH3 group in each carbon atom, and it can have several conformations like this, right? So when you draw an energy diagram, you will get something like this, where you have now in the earlier case, you have the same upper energy and the lower energy. But here, the energy levels are different because you know when the CH3 groups are eclipsed, that is one behind the other, you get the highest energy level, right? That is not very stable. That is the least stable structure. But when you have these CH3s far apart, one pointed upwards and the other one downwards, you have the lowest energy, right? So you can understand where this, if you look at the structures, D is the compound where you have these CH3s away from each other like this, right? So this is the energy gap between the most unstable and the stable structure is about 21 kilojoules per mole, right? So a simple question here. Try to work it out. Okay, I was checking your messages in the chat. CRC class එක කොයිද තියෙන්නේ? Room 11, CRC 11 upstairs. And you have to check this screen, the display. They are displaying the places where the the schools are conducted downstairs, the ground floor. Okay, hope you have enough time to work this out. Very simple. Select the correct statement regarding statement or statements regarding the above conformations. So it says most stable conformation is A. Is it correct? Can somebody answer?
Yes, madam.
Yes, madam.
Yes, it is correct. Because you can see it's obvious, because these CLT chlorine atoms, methyl groups far apart, right? So B is less stable than C. Is it correct or wrong?
Wrong.
Wrong. It
Wrong.
is wrong. And again, C is less stable than B. It is wrong. And the last statement is correct. Stability of B and C are the same. So when you go around the molecule from one end to the other, it's the same arrangement line. B and C are having the same arrangement. ClCl, Me, ClCl, Me. So it's only the place where it is drawn is different, right? But the arrangement is the same. Right, so we hope you have gotten some understanding about the stability of the conformations. Okay, so
Excuse me, madam.
yes,
Madam, then here when we consider a molecule as the most stable one, the same atom should be very far from each other.
yeah,
Is it like that?
not
thank
like
you.
that. You have to consider about the diaxial interactions. Axial, when one group is behind the other one, you have to consider the size of the group. If it is a large group, the repulsion is more. If it is a small group, repulsion is less, right? So when you are having many different groups, you have to consider the size of the atoms or the group size of the groups and the interactions between them, right? So we'll be doing one exercise on this cyclohexane. So we will get the idea clearly when we are discussing. Okay, so next we'll consider the conformations of cyclohexane. Now, all this time we were talking about linear molecules, ethane, butane, like that. And cyclohexane is a cyclic structure with 6 carbon atoms. And on paper, normally we draw like this, 2D representation of cyclohexane. But you know, when actual molecule, the structure of the actual molecule in 3-dimensional space is this one, not a flat molecule, but a molecule like this. Look at the stick and ball model of this cyclohexane. So it is 3-dimensionally attached. The structure, you have 6 carbon atoms. Here you have another carbon behind that, 3 here, 3 here. And you can see all the carbons are having a tetrahedron arrangement. So all these hydrogens and bonds are having the same bond angles, right? So if you draw it on paper, you can draw something like this to show the 3D arrangement. But still, when you are drawing it on paper, you can't actually show, it's difficult to show the actual 3-dimensional stereochemical arrangement. But something like this give you some idea how the atoms and bonds are there, right? So this is called the chair conformation of cyclohexane. It's like a chair, right? So you can see in this 3D model also, one point is below and the other one is pointed upwards. right? So there are two types of hydrogens here. This is called equatorial hydrogen, and these which are vertical called axial hydrogens, right? And axial hydrogens and equatorial hydrogens are interconverted in the two-chair conformation. Now, this molecule, it doesn't stay like this. When you have molecules, they can rotate or bend or twist, right? So when you are having cyclohexane in a jar, these molecules do not stay like this all the time, right? They can, when you supply heat, changes can happen, right? Depending on the energy you supply, so many different twisting, bending, and everything can take place, right? At room temperature also, they can take automatically the changes in the molecules, right? So in cyclohexane, these two, this is one chair conformation. It can be converted to another chair conformation. If you look at the small video here, look at how it is changing. So you can see at one position, some hydrogens which are axial are going to be changed into equatorial, right? Now blue hydrogens are axial and they are going to be equatorial, the other conformation, other form. So in between the two chair conformation, you have several different conformations. So hope that you have the understanding. Shall we stop at this point? So it's going on like this, right? So we'll stop it here. So you can see now I have an energy diagram for different conformations. So as I said, it has two chair conformations. Chair like this, one chair is shown here, and when during the conversion, you can have a board conformation, and then it takes a half chair conformation and a twist board. Like that, you have different names. You don't have to bother about those names, but only thing you have to understand is these different conformations have different energies, right? So if you draw a diagram like this, you have the chair, both chair conformations are having the least energy, and which they are the most stable conformations. Okay, so cyclohexane, how to draw cyclohexane properly on paper. I'm going to teach you how to draw properly, because I know always I come across when marking the exam papers, most of you don't know how to draw. That is why I have included this slide. Otherwise, we never thought of teaching this, because this is not something to teach you, right? But anyway, since you are drawing them in a wrong way, I have included this slide. Let's see. Now, this is how you draw the two chair conformations. You can see one chair is like that, and the other chair is like that. So this end bends down, and this is lifted down, the other chair conformation. So remember, all the carbons are having a tetrahedron structure. You saw that in the stick and ball model, right? So how to draw? Now you start drawing. The step one here is you start drawing two parallel lines like this. And then step two is you have to draw another two parallel lines from this end and the other end, right? And then you connect, the third step is you connect the two sets of lines like this, and you get the chair conformation. Then you can draw axial hydrogens, vertical ones, and then equatorial one, right? Now, when you are drawing, start drawing the cyclohexane structure by drawing two parallel lines. Otherwise, you will draw some butterfly-like structures, which are incorrect, right? Most of you like right? Butterflies, they look like butterflies. So that is wrong, right? So when you start drawing by drawing two parallel lines, it will not go wrong. So another question. Look at it. Now you know how to draw chair conformations, but there's some extension in it to it. It has not only hydrogens but has two substituents, bromine and CH3, which is then once you have drawn the structures, chair conformations for both, you have to find out the most stable chair conformation for both compounds, right? So if you want any help, you can go through the book. So once you try it out, I will explain how to draw and how to find out the table. So I'm giving you a few minutes. Go through your lesson material and try to draw the chair conformations. I'll give you 5 minutes. Okay, I think I have given enough time. Enough means I don't think that you have everybody has come up with the answers. But anyway, I wanted to give you some time to think and go through the book. And everything is there in the book. Don't think that we are giving you questions out of the book. Everything is there. Let's see. Now you know here what is the difference between the two molecules here. The attachment of CH3 group is different in both molecules, in the two these in the pair, right? So one is now these dotted broken lines indicates that it is towards the away from you, and the solid line means it is projecting towards you, right? So let's see how to draw. Now there's no problem drawing the chair conformations. Right now, you know how to draw a cyclohexane structure, the skeleton, right? It's like this. Okay, it's like this, right? One chair conformation is there. So to help you how to draw, how to attach the substituents. Now, this means Br is joined to the carbon with a solid line. That indicates that it is projecting towards you, right? And the other one is going away from the plane of the paper, going away from, directed away from. So when you are drawing, indicated that on paper for a cyclohexane chair like this, you imagine there's an imaginary horizontal line. So the bonds drawn below the line are away from you, and bonds drawn above the line, this carbon bromine bond, it is above the line, above the horizontal line. That indicates that it is pointing towards you. So to learn that, learn this concept, when you are drawing, have an imaginary horizontal line, horizontal straight line. Below are the ones which are projecting away from you, and above the line is projecting towards you, right? So one structure is like that. This is the imaginary line, right? So for the other one, you can draw one structure like so, like this. Now here, if you take this molecule, this Br is the solid line above the line, and the other one is below the line, because these two are different, right? One is above and one is below. And in this structure, this is only one chair conformation. And you can draw one chair conformation for the other structure also like this. Here, in this case, both groups are pointing towards you. So both should be above the imaginary line, right? So in this case, it is cis, opposite to each other. In this one, in the second molecule, it is cis because both groups are on the same side, right? So this is only one structure. Let's see the other chair conformations. Now for this molecule, this trans structure, you can draw as I have drawn earlier. You can draw a structure like this, where both bonds are equatorial. This symbol E means equatorial, right? They are at an angle, not straight, right? Not vertical. So both groups are drawn with equatorial bonds. And the other chair conformation, in this conformation, you have both axial, right? Both axial, because this is the imaginary line. You have to draw the CH3 group below the line. So when you draw below the line, it is going to be axial. And this one above the imaginary line. So here you have the imaginary line along this vertical, this one horizontal line, and above the line is a axial bond, right? So in one conformation, one chair conformation, both groups are equatorial, and in the other one, you have both axial. Now find out the correct places to put the groups. Now if you number this carbon with the bromide as carbon number 1, 2, 3, 4. CH3 is at the 4th position. So 1, 2, 3, 4. The places where we have put the groups are correct in all both chairs, chair conformations, right? Now look at the structures, these two structures. How to find out the most stable and less stable structure, right? When you look at this one, this chair conformation, you can see bromine and hydrogen are close to each other. And here CH3 group is also a large group. Bromine atom is also larger than hydrogen, right? So when they are like this, the diaxial interactions, we call them diaxial interaction because this hydrogen is axial, this CH3 group is axial. Here hydrogen is axial, bromine is axial. So they will have 1,3 diaxial. Why you call it 1,3? When you consider this one carbon as 1, this is 2, this is 3. At 3 position, you have hydrogen. So 1,3 diaxial interactions are there. And if you consider this carbon as 1, 2, 3. Again, at 3 position, you have hydrogen. Or else you can take 1, 2, 3. Again, you have a hydrogen here, right? It is not drawn that hydrogen also can have 1,3 diaxial interactions with the other CH3 group, right? So same way, you have another hydrogen here, like that all the hydrogens will have 1,3 diaxial interactions with the groups. So it makes the conformation less stable, right? And whereas in the other compound, you don't have such diaxial interactions because they are all equatorial groups. Both groups are equatorial. So you don't have this diaxial interaction, only hydrogens and hydrogens are there. So the interactions are minimum, right? So let's take the other compound.
Hello, madam.
Yes.
Second confirmation එකේ මේ anti clockwise මේක අපි mark කරන්න ඕන 1 2 3.
Anyway, right? So you consider one position as 1, take one carbon as 1, and then keep on counting this way or this way. Now here, since it is 1, 3, 4, you have to have at these 2 positions. You can put bromine here even, right? No, it is not necessary to put a bromine in this carbon atom, right? You can put bromine here also. So when you put bromine here, you can, since it is up above the paper, you have to have axial bromine. And where do you put CH3 then? If you have bromine here, CH3 should be 3 carbons away. So 1, 2, 3. No, if you have bromine here, 1, 2, 3, 4. Here, if you put bromine here, you have to put CH3 here. Since it has to be below the paper, it has to get an axial position, right? So you can start with any carbon atom because in this molecule, when you make a model, you can rotate it, turn it on your, if you keep the model on your palm, you can turn it any side. So in a solution, these molecules can turn any, can get any position, right? So they are not going to stay like this in a solution, right? Though we put it on paper like this, right? So here also, if you want to put bromine here, you can put bromine here. But only thing is, since it is above the plane of the paper, you have to put it as an equatorial bromine, right? So only thing is, you count the number of carbons and put the other group in the correct position, right? So hope you have got the answer.
Yes, madam. Thank you.
Right. Now take the other molecule where you have both groups cis, same side, right? So if we consider that this is projecting upwards, solid line. So in this conformation, you have put CH3 like this. This is the imaginary. Here you have an imaginary horizontal line. Above it you have CH3, so that it is axial CH3. So 1, 2, 3, 4. That is 1, 2, 3, 4 here. You put the bromine to make it above the plane of the paper. This is the imaginary line. You have to draw a equatorial group like this. So both these are above the plane of the paper, same side, right? So the other chair conformation is where you have now, if you have this end up here and this end down, you have to turn both ends the opposite side. So this is down and this is up. So when you have bromine above the plane of the paper, you have like this axial one, and here CH3 group becomes equatorial, and again these are on the same side above the plane of the paper, right? So when you consider the two groups, diaxial interactions of the groups of two chair conformation, here you have CH3 group and a hydrogen having 1,3 diaxial interactions. And in this other chair conformation, you have bromine and hydrogen having 1,3 diaxial interactions. And when you compare the size of the two groups, bromine is also comparatively, when you compare with hydrogen, it is a larger atom. But when you compare with the CH3 group, you have carbon and 3 hydrogen atoms around the carbon. And when you compare the size of the two groups, the CH3 is going to be larger, right? And this conformation both have diaxial interactions, but the diaxial interactions in this chair conformation, where you have CH3 hydrogen, 1,3 diaxial interactions are more. So because CH3 is bulkier than bromine. Bulky means larger. And this is the less stable conformation compared when you compare with the other one. So hope you have learned now with this, by giving this exercise, I wanted to teach you how to draw chair conformations for cyclohexane with substituents attached to it, and how to find out the places where you are going to attach the groups, and how to draw equatorial, how to draw them properly when you have axial, when you have trans arrangement and cis arrangement, and how to decide whether it is equatorial or axial. And then lastly, I wanted to teach you what conformation is going to be more stable and which one is going to be less stable. And out of the less stable conformations also, how to find out the least stable one and the most stable one by considering the type of the 1,3 diaxial interaction. So let's move on to the other one. And we are going to learn about stereoisomerism, means alkenes. Now, you know, alkanes show conformation. You saw that this one, when you have a single bond, carbon-carbon single bond, they can rotate and show conformational isomers. And in alkanes, you have a double bond. So this is the structure of the alkane. You have pi bonds, the p orbitals forming a double bond. You have the sigma bond and a pi bond, right? These p orbitals giving rise to another pi bond, right? So they have carbon-carbon double bond. So in the geometrical isomers of alkenes, you have the same molecular formula, have the same order of attachment of atoms, but differ from the way the atoms are arranged in space, the space. And alkanes exhibit geometrical isomerism because carbon-carbon double bond cannot rotate along its axis, right? So in alkanes, free rotation, but in alkenes, no, the double bond around the double bond, the molecule cannot rotate, right? So, yeah. Now, let's see what a stereocenter is. Before identifying the stereocenters in the alkenes, we'll see what a stereocenter is. Actually, that is the place which is responsible to show the stereoisomerism, right? The place or the atom or the place which is responsible for showing stereoisomerism, right? So there are two types of stereocenters. One is trigonal planar stereocenters that you can see in cis-trans, that is also called cis-trans or EZ isomeric, right? And you can see this in alkenes. That is why I have included this slide to show you, give you the idea what type of stereocenters are there. So in alkenes, you see this type of isomer. And the other type of stereocenter is a tetrahedral stereocenter, where you can get an asymmetric carbon, or it is also called chiral carbon. And there's a small way of finding out the number of stereoisomers for a molecule. Now you saw for thalidomide, you saw 2 isomers, R1 and S1, right? Our drug molecule. When you have several number of stereocenters, molecules, now thalidomide had only 1 stereocenter, but molecules can have several stereocenters. Maybe they are trigonal planar or tetrahedral. If you know the number of stereocenters, you can find out the number of stereoisomers by this formula, 2 to the power n. N is the number of stereocenters. So before drawing any isomer, you can find out the number of stereoisomers by putting it into this the equation, 2 to the power n, right? So that is very simple. So with that idea, we'll try to work this out. How many stereoisomers are there for the following compound? Draw and label them. Now, to have a stereo center in an alkene, around the double bond, you have to have different groups, right? Now, this is an alkene, and the double bond is here. And in this carbon, you have a CH3 group and a hydrogen. And here also hydrogen and a CH3 group, right? So I will, without giving time, I will show you how to do that. So the stereo center here is this double bond. I have put it in an asterisk. I have marked, right? And you can calculate the number of stereo centers in this molecule, for this molecule, like this. As I said, number of stereo centers is 1. Yes, Buddhika, what's your... Somebody raised the hand? Okay, so the number of stereoisomers for this molecule should be 2 to the power n. N is 1 because 1 stereocenter. 2 to the power 1 is 2. So you should be able to draw 2 stereoisomers for this molecule. Let's see how. Like this. You can see each carbon has a CH3 group and hydrogen. So you can draw one structure with the CH3 groups like this on the same side and hydrogen on the other side. And you can draw another structure with the CH3 groups in opposite sides of the 2 carbons. So according to the formula, you get 2. So correct. So there are no other ways of drawing. You can't draw any more structures. Only possible structures are these 2, right? So we call this, when you have the groups on the same side, CH3 same side, hydrogen same side, you call it cis. Can you remember learning these things at level 3? And this is called, the opposite of it is trans, right? So hope you have understood how to draw, and you know this is the stereo center in this molecule, which gives rise to 2 stereoisomers, and these are called geometrical isomers, right? And or else cis trans isomers, right? Okay. Now you know. Let's go back to the previous one. Now you know, when you consider this double bond, you think that this is fixed, right? In both the carbons, this is fixed, right? CH3 on top and the hydrogen is below. Same here. And when you change these things, you have to get a different structure. When you shift this CH3 down to the bottom, this one, the 2 bonds are changed, you get a different structure, right? So that you can, if you have an alkane like this, and if you want to find out whether it is showing stereoisomerism, try to change the group above and below, and it is going to give you a different structure, right? So that if you are getting a different structure, definitely it is showing stereoisomer, right? So with that idea, try to solve this, try to select the compounds showing geometrical isomer. Can you please mute your mics? You have 4 structures. Just now I have mentioned how to find out whether the stereoisomers are there. Just change the groups attached to one carbon atom and see whether you are going to get a different structure. Okay, hope you have done it. Now it's very easy. As I said, just keep one carbon, the groups static without changing, and change the other 2 and see. Now you change this one. Well, look at this compound K, change CH3 group here and put hydrogen here. So here in this molecule, you have CH3 and the other carbon has the cyclic attachment, and where you have this chlorine very close to CH2. When you change, you get here and hydrogen comes down. Now the arrangement is different, right? Hydrogen here and hydrogen and chlorine close to each other, and CH3 is far away, right? So it will have geometrical, it will show geometrical isomers. Look at this compound. You keep this static, don't change. Change the groups of the other carbon. You put chlorine here, CH3 up. Same thing, because the environment is of the other carbon is the same. Same thing, no change. You put CH3 here, slowly in a similar compound. So no geometrical isomers. And M, molecule M, keep this one unchanged, change this one, CH3 down, Cl up. Then what do you think? It is different now. You get CH3 and hydrogen on one side, Br and Cl on the other side, a different molecule. N molecule. You have bromine, bromine. So when you change also, nothing happens. You have CH3 and bromine one side, Br and hydrogen one side, on one side. So no change. So this doesn't show geometrical isomerism, and this one doesn't show. So my answer, only K and M shows geometrical isomerism, right? So hope you have understood what the idea. Okay. Now, designate this is your level 3 knowledge. Designate the configuration of the double bond of the following compound. That's very easy. How to do that? According to Kahn-Ingold rules, you find out the priorities of groups. Okay, when you are going, now for that you have to go along. Now you consider consider the two carbons on either side of the double bond, not this carbon and the two groups, and this carbon and this carbon, the other group, not these two groups on both carbons. Consider one carbon at a time and the two groups attached to that carbon, right? So when you get hydrogen and CH3, you get higher priority for this one. And when you have Br and CH3, you get higher priority for did I miss? Yeah. Okay. So here you get higher priority here. Okay. Now earlier we have done cis-trans naming because you have similar groups. But when you have four different groups like this CH3, CH3Br, you can't have this cis-trans, right? So for that we apply this Carnin-Gold pre-log rules and find out higher and low, right? You have consider the groups and identify the groups which are having higher priority among one carbon atom, and you select the higher priority group from the other carbon atom, and when they are on one side, higher priority groups are on one side, you call it Z, and when they are opposite to each other, you call it E, right? These are some Latin words, susamen and interjection, right? So if you look at this example, the two groups on this carbon atom is bromine and CH3. Bromine gets the higher priority. You consider the atoms one by one. Now, when you consider the group, first atom is this one. So we have to compare bromine and carbon. So out of bromine and carbon, bromine gets the higher priority. So we put number 1 there. And here you have two carbons, right? Similar. Then we go to the next atom. So in this case, you have carbon, and in this case, you have oxygen. So out of oxygen and carbon, oxygen gets the higher priority. So you put 1. So when they are on opposite side, it is E. And here, another example, you have CH3, CHO group here, and a CH2OH. So carbons similar. Next atom of a difference is oxygen here and oxygen here, right? And when you have an oxygen, double bonded oxygen, you know you have to open up the bonds and attach when you another oxygen to the other bond. You have when you have doubly bonded oxygen, you open it and attach another oxygen, right? So when you do that, since this is similar, we go to oxygen, here again oxygen, and then we have to decide what is getting the priority by considering the other oxygen attached to this carbon, what we have attached by opening the double bond. So this gets the higher priority. And here, same carbon, next is Cl, Br. Out of Cl and Br, Br is high atomic and get the priority. So it is Z. When you have a higher priority group on the same side, it is Z, right? So we hope you know, now you already know how to do that, right? So we'll get our previous question. Question is, cis-trans is not possible here because bromine is different. If we had a hydrogen and CH3, it is easy, cis or trans. But here it is bromine and CH3 and hydrogen and CH3. So that we adapt this Carnin-Gold pre-log rules. According to this, we have to find out the groups which are having higher priority. So it will be like this when you consider the two groups here. This one gets the number 1, 2 here, and bromine gets number 1 over carbon. And then if since they are on the same side, it is Z and it is Z. So draw the other isomer of the compound. Draw the Z isomer. Draw the E isomer of this compound. Can you draw? You just have to draw the Z compound, opposite side. And this is the compound which you are going to draw. Keep two groups of the carbon atom unchanged and change the groups of the other, interchange the groups of the other carbon atom, so that you get the E isomer. So hope you are clear with these geometrical isomers. So I'm not going to do this exercise. It will take time, but because you are now very familiar with this EZ nomenclature, which you have learned at level 3. So refresh your minds by reading the previous book. Right? Okay, so answers are there. I will upload. So you do it yourself and find out. And you will, for your paper, sometimes you will get compounds with several stereo centers. Here, for example, in this compound, you have 2 double bonds and both are stereo centers because they are these double bond is carbons of the double bonds are attached to 4 different groups. So that this is a stereo center, and here also the same, another stereo center. So it has 2 stereo centers, and for each stereo center we have to designate whether it is Z or E. Okay, so let's see what chirality is. Actually, chiral is a Greek word and it means handedness, right? So if you look at, and the meaning is having a non-superimposable mirror image. Handedness is having non-superimposable mirror image. Actually, the meaning of chiral is having a non-superimposable mirror image. Why it is called handedness? Because you know, these are the images of the pictures of your left hand and the right hand. You cannot superimpose left hand on the right hand. You can't bring this left hand here and superimpose. You can see it is not superimposing, right? So this mirror left hand is the right hand is a mirror image of your left hand, and they are not superimposable, and that is called chirality. So if any molecule is a chiral molecule, that means we have molecules which are having mirror images which cannot be superimposed. So what is a chiral carbon atom? It is an asymmetric carbon atom. You know the word meaning of the word symmetric and asymmetric. Symmetric is samamitika, asymmetric is asamamitika. So asymmetric carbon atom is a carbon atom attached with 4 different groups. So any molecule having a carbon atom with 4 different groups attached are said to be having a chiral carbon atom. So that carbon atom is called a chiral carbon atom. All 4 groups are different. So what is a chiral molecule? So chiral molecule is a molecule which is having a asymmetric center. It's an asymmetric molecule, or a molecule with no center of symmetry, or no plane of symmetry, or no axis of symmetry, right? Sometimes the molecule may be having chiral atoms, they are asymmetric carbon atoms, but overall, when you consider the molecule, it may have a center of symmetry or a plane of symmetry or axis of symmetry. So when you go further during our discussion, you will see this phenomenon, right? So it has to be a asymmetric molecule, right? So the best way to understand is a chiral molecule is a asymmetric molecule, right? So what is the importance of this asymmetric this thing? So this is the Nobel Prize winner. These are 2 other Nobel Prize winners of 2021, and they got the Nobel Prize awarded for their work. on development of asymmetric organocatalyst, right? So you can go through this one and get an understanding what they have done. So see, this area is given rise to winning the Nobel Prize also. Right. Now you have some understanding what is chiral, and the opposite is achiral. Chiral is having a asymmetric center, no symmetry. Achiral is symmetric. Like, don't get confused. Chiral is a molecule which is having 4 different groups, or asymmetric molecule, right? So to get this under get this meaning understood properly, we'll try to work this out. This question. Here you have 5 molecules. State whether the following molecules are chiral or achiral. Look at them carefully. Consider the groups attached and find out whether they are chiral or achiral. 3 minutes. In the meantime, please enter your registration number, name, and the center. Main thing you have to understand is the molecule should be asymmetric. Okay, let's see now. Now take the first compound. It has four groups, but they are not different. You have a hydrogen, two hydrogens, similar groups, right? So when you have, when you don't have two different groups, they are not going to be chiral. So it is called achiral, not asymmetry. Right. The second one, you have three carbon atoms, 4 carbon atoms. And when you look at the structure, you have this carbon and another carbon, both are asymmetric, right? So when you consider this carbon atom, it has this CH3OH and OH and a large group like this, and this carbon atom, Br and CH and H and a large group like this. So it is going to be asymmetric and chiral. Take the third compound. Now you have double bonded carbons here, carbon skeleton here, and along now you can see this one. When you don't have solid or broken lines, that means these groups are on the plane of the paper, right? And when you have like this, it means this one is pointing towards you and this one is pointing away from you, directed away from you, right? These are on the plane of the paper. So here we can't find out whether the carbons are symmetric or asymmetric because no 4 groups are attached. The two groups here and a double bond, no groups here. Again, this one has 2 groups and a double bond. So we can't find out whether a asymmetric carbon is there. But you can find out whether the whole molecule is symmetric or not. Whether it is the whole molecule is symmetric or asymmetric. Right. Now consider this this molecule and this hydrogen and methyl. We are going to cut the molecule along the paper of the plane of the paper from the middle of this molecule, right? So when you cut with a knife, you can cut half of the hydrogen and cut half of the methyl group, and everything cuts into halves. And on one side you have half of the hydrogen, and on one side you have half of the methyl. And from here you get 1 whole chlorine on one side and 1 whole chlorine on the other side. So it has a symmetry, right? Now you have to consider the arrangement, the stereochemistry of these bonded groups, right? So this is when you cut it along the plane of the paper, right? When you cut the molecule along the plane of the paper, you get 4 similar parts, 2 similar halves. So it has a center of symmetry, the axis of symmetry or plane of symmetry, and it is going to be achiral. And same way you can think for this molecule. But not along the plane of the paper. Now take this molecule. When you cut it along the plane of the paper, it's all right. It will, this part will cut symmetrical. Part of NO2 and part of the ring and part of NO2 on the other side. But when you cut it along the plane of the paper, 1/2 is going to get a chlorine and the other half is going to get a bromine. So you can't cut it from that plane, right? So, but imagine if you are cutting 90 degrees right angle to the plane of the paper, right? So you will cut half of the bromine. One half of the bromine is on upper side and the other half is on the bottom side. And same way, chlorine is also cut into 2 halves, right? And the molecule here will, when you cut it along this plane, you get 1 nitro group with a part of the benzene ring here on the one part and 1 nitro group and the rest of the molecule on the other, right? So it has a symmetric axis, a plane of symmetry again, right? Imagine not along the plane of the paper, 90 degrees right angle to the plane. So that means you cut bromine and chlorine across the atoms to get half of bromine and half of chlorine, right? So it has a plane of symmetry and it is going to be achiral, right? Not chiral, not asymmetric. Not asymmetric means achiral, right? And look at the other molecule. You have a similar thing, but when you cut, now when you cut it along the plane of the paper, also you get two different halves. When you cut it along right angle to the plane of the paper, also you get two similar halves, two different halves, right? Because you have CO2H and Br here, and Br and CO2H here. So benzene ring is having similar groups, so that you get two different halves, and it is going to be asymmetric and a chiral molecule, right? So hope you got the idea what chirality and achiral, or what chiral and achiral molecules are, and how to find whether they are chiral and achiral. So what are enantiomers? Now you have come across the word enantiomers. You may be knowing by now, they are actually the mirror images of each other. So if a molecule is having another molecule which is similar to its mirror image, they are called enantiomers, right? Now look at this molecule. Right here I have, now look at, we just consider this as the yellow one, red one, and green and white one as different groups. So this one has the mirror, this one is the mirror image of this one, and they are enantiomers. We call them enantiomers. Enantiomers are the stereoisomers whose molecules are mirror images of each other. Enantiomers are chiral molecules. Why and how? Because you have the center carbon atom in the center and four different groups here. So asymmetric, and same, the mirror image is also the same. They are asymmetric molecules, and we also call them chiral molecules, and the chiral carbon atom is this one, right? So those two are enantiomers, right? So what are diastereomers? Diastereomers are the stereoisomers which are not enantiomers, right? Now we were talking about enantiomers for this compound where you have only one carbon atom, right? But when you have several carbon atoms, right, and when they are not enantiomers, there can be other isomers, right? So in that case, stereoisomers which are not enantiomers or not mirror images of each other are called diastereomers, right? Now look at, now I have indicated here what the pairs of diastereomers. Now when you consider the molecule number 1, and let's select this green one, the molecule number 3, right? To the pair 1 and 3, right? Now you have CH3, CH. Okay, let's first identify the mirror images or the enantiomers. When you consider the molecule number 1 and molecule number 2, you can see they are the mirror images. You have hydrogen and chlorine one side, and opposite side you have hydrogen and chlorine here, and this is OH and hydrogen here, OH hydrogen. So they are 1 and 2 are mirror images of each other. And when you consider 3 and 4, they are the mirror images. Chlorine, chlorine, OH, OH, other side, hydrogen, 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 hydrogen. You don't have to consider the top and bottom one, they are the same, right? So 1 and 2 are enantiomers, and 3 and 4 are enantiomers. But what are 1 and 3? They are diastereomers. Why you call them diastereomers? Because when you consider this carbon atom, it has chlorine and hydrogen, different arrangement here. But when you look at the other carbon atom, the same arrangement, but this is different. They are not enantiomers because this is different. This carbon has a different arrangement. They are not enantiomers, so that we call them diastereomers. So same way, 1 and 3, 1 and 4. take 1 and 4. This arrangement here in this carbon atom is the same, but it is different on the other carbon. So they are not mirror images, but they are called diastereomers. Same way you can identify the other pairs. Then they are not mirror images. So when you compare 2 and 3, they are not mirror images, but they are diastereomers. So when you go on working out the problems, you will identify. So there are some past papers uploaded in the library site and in Learner USL also under past papers and pet papers section. You work out the questions on stereochemistry and identify, try to understand more. Okay. So another, the diastereomers, the geometric isomers are also a type of diastereomers, right? We put the geometric isomers, what we have learned a little while ago, are also diastereomers. We put those also into that category. So you can see this is the 6 arrangement, trans arrangement of this one. They are also coming under the diastereomers category, right? So what are mesoisomers? Mesoisomers are the compound which has several stereocenters. The compound should have several stereocenters, not only one, but molecule is achiral due to the presence of a mirror plane or plane of symmetry. Achiral means no symmetry, there's a symmetry, so there's no chiral center. The molecule as a whole is not chiral, but achiral, because there's due to a presence of a mirror plane or a plane of symmetry or plane of axis of symmetry. Now look at this molecule. When you consider the molecule along this axis, it has a symmetric arrangement, right? OH here and H here, OH here and H and CO2. So this is a plane of symmetry in this molecule. So this molecule, though they are individual carbons are asymmetric. Consider this carbon, it has 4 different groups. This large group, OH, CO2H and H, and this carbon also has a symmetric chiral carbon atom, asymmetric chiral carbon atom, CO2H, OH and H, and a large group. But molecule, the whole molecule, not a carbon atom, molecule has a plane of symmetry. So when you bend the molecule from this axis, you get 2 similar parts, right? So they are called mesoisomers, right? So another example is here. You can see the plane of symmetry is this one, this gray color one. So when you cut the molecule along this axis, along this plane of plane, you get this part and this part similar, and this carbon is going to cut into a half, and a chlorine and hydrogen are also going to cut into halves, and 2 similar parts are obtained when you cut the molecule along this plane, right? So they are called meso compounds. But separately, this carbon is asymmetric, and this carbon is also asymmetric, and they are having 2 chiral centers, but the molecule is achiral and called mesoisomers, right? So an exercise here. Now it's a very simple one. Simple means now it's based on all what you have learned up to now. How many stereoisomers are possible for the following compound A? You try to work the rest of the things together, but the first part you can attempt. Now I told you there are 2 types of stereocenters. One is trigonal planar. Trigonal planar one is the one with the double bond. Double bond with both carbons attached to 2 different groups. Each carbon is attached to different groups, so that it will give rise to isomers, right? Depending on the arrangement. And the other type of stereocenter is a tetrahedron stereocenter, where carbon is attached with 4 groups, and the 4 groups have to be different. So that carbon is a asymmetric carbon atom. So you can expand this structure and find out the number of stereocenters in the molecule. You work out the first part alone. We'll do the rest of these things together, right? So first identify the number of stereocenters, and then only you can put into that 2 to the power n and find out the number of stereoisomers. So first try to identify the places where the stereocenters are. Okay, now let's see how to find the stereocenters. Now consider, now we said there are 2 types of stereocenters. Take this carbon atom. Is it a stereocenter? A carbon to be a stereocenter, 4 different groups should be attached, right? So it has 3 hydrogen atoms. So it is not a stereocenter. Take this carbon atom. It has a double bond, not a tetragonal stereocenter. But you have a double bond here, right? And the carbons have CH3 group and a hydrogen here. And this carbon has a hydrogen and this one very large group, different group. So that this double bond is going to be a stereocenter, trigonal planar stereocenter, where you have 4 different groups attached. Hydrogen and CH3, hydrogen and this big group. So one stereocenter we have identified. Consider this carbon. It has this part, it has hydrogen and another carbon with this one. And it has 2 hydrogens here and 2 carbons attached, right? So 2 hydrogens are similar, no? So we can't consider it as a asymmetric carbon because there are 2 hydrogens. So consider this carbon, next carbon atom, where you have a hydrogen, carbon attached with another large group, bromine and another CO2 group. So when you expand it and draw, you can have carbon, bromine, CO2H group, hydrogen, and a big group here on the other side, right? So it has 4 different groups. So this is going to be a stereo or a chiral carbon atom, a stereo center or a chiral carbon atom. So overall, this molecule has 2 stereo centers. So how to find out the number of stereoisomers? 2 to the power 2. Number of stereo centers are 2, right? So 2 to the power 2 is 4. So you should be able to draw 4 different isomers for this molecule, right? So our next part of the question is number of possible stereoisomers is 4. Draw the stereoisomers of A using Fisher projection formula to show the stereochemistry at the chiral carbon atom. Label them as A, B, C, and C, etc. This is one of the final exam questions, right? I have taken it from a past paper. So these are the type of questions you are getting under this stereochemistry. So you have to draw all possible stereoisomers, all 4, according to the Fisher projection formula. Show the stereochemistry at the chiral carbon atom, and you can label ABC, right? And then the second part is identify a pair of enantiomers and identify a pair of diastereoisomers or diastereomers. Right. Now let's work together. Now this is the molecule. So to make it easy, I have now what they are asking is a Fisher projection formula, right? So when you are drawing the Fisher projection formula, you normally know you draw a vertical line and indicate the other ones in horizontal line. So in this case, you have now you have this large group with a double bond. You can indicate it like this, right? You have to, either you can put a straight line here, but when you put a straight line here, it is difficult to indicate the other one. So I have put it at an angle. So one structure is this. So it is starting from with this carbon atom. If you start it from here, you have this double bond, CH3 and H. This carbon atom is the next carbon atom here, and it has a group, large group like this. So you have a CH2 and these 2 groups. This large group and this one, which is the bend here, has 2 hydrogens, right? So this is one structure. So like that, you can draw different structures. Now see, we'll keep this unchanged, this part unchanged, right? This the double bond unchanged, right? So it is the same here. Only difference is we have changed the place of the bromine atom. Attachment of bromine is different in B. And then in C, we have changed the 2 groups around the double bond. So here in this one, consider A. According to A, we have changed it to the top, CH3 on the top and hydrogen below. And this one is not changed. This part is not changed, the same. And the other structure you can draw is, you can keep this one unchanged, but change the bromine of the place of the bromine. So it is like this. You have this top part from the second molecule and the change one here. So that is how you draw 4 structures, 4 different structures. And the 2 stereo centers are this one and this one. And you can see it is different in each of them, right? So these 2 are, now when you are drawing enantiomers, you don't consider the double bond part. It is only the trigonal planar carbon atom which is considered when you are drawing enantiomers. When you are considering whether it is a mirror image, don't consider this part. So it is consider the arrangement of this double bond, right? But the group should be to the same side, right? Group as a whole. right? Otherwise, people, what we do is to change this one also to the other side. If you draw it to the other side, it is wrong, right? Because this is considered as a whole group, right? So in this one, you have bromine here. Consider only the trigonal planar. Consider only the tetrahedron carbon. So here, enantiomer has the opposite arrangement. Bromine here, hydrogen here, and opposite arrangement is hydrogen and this one. If you keep a mirror, you can see this part is the mirror image of each other, right? And these two are also separately mirror images. When you keep a mirror in the middle, this part is going to be the mirror image of each other, right? So these are enantiomers. And what are diastereomers? Now, when you consider A and C, they are not enantiomers, but diastereomers. When you consider A and D, they are not enantiomers, but diastereomers. And same way, B and C and B and D are mirror image, in a diastereomer isomers. They are not enantiomers, right? So when you go through the book, you will come across a lot of examples. So hope you got the idea how to find, how to draw the enantiomers and how to draw the diastereomers, how to identify the diastereomer isomers. So the calculation is very simple. First of all, you have to identify the number of stereo centers. Okay, so now we know tetrahedron carbon atom can be a stereo center when all four groups are different. All four groups attached to that carbon are different, right? And how to name, now how to identify. Now these two are enantiomers. This is the enantiomer of this one. So how to identify them separately? You have to way of naming, or you have to name them separately, or we have to have a way of identifying the difference, right? So people have introduced a system to name the compounds, and it is called RS system of nomenclature. To do that, you have to follow a Kahn-Ingold-Prelog convention to designate the configuration of the chiral centers. Okay, sorry about it. So there should be a systematic way of naming the compounds, and that is RS system of nomenclature. And it is done according to Kahn-Ingold-Prelog convention, right? We'll see how to name compounds using this convention. And the way we do is naming the system like R and S conformations, right? Right. Now, I'm going to do it as an exercise. Find out the configuration of the following chiral molecule. Now you have a molecule here. You have a carbon, hydrogen, chlorine, bromine, and iodine attached. Very simple molecule. All four groups are different, and this carbon is a chiral carbon atom, chiral center, and it is a stereo center because all four groups are different and an asymmetric carbon atom. Right. Now, how to find the configuration according to this, right? So first of all, you have to follow some steps according to the order given here. Number the groups in the order of priority. Yeah, you are not going to name whatever the way you want. You have to give a priority. You have to follow the priority order. And then priority order is the highest atomic number gets the priority, highest atomic weight, right? Number the groups in the order of priority, and then turn the molecule to project the lowest priority group away from you, right? So keep this in mind. When we are doing, you will get it, you will grasp the things clearly. Number the groups according to the priority, and then you turn the molecule to get the lowest priority group away from you. And then the third step is find the direction of reading the 3 groups from 1 to 3. Now we have labeled according to the priority order 1 as 1, 2, and 3. So try read it 1, 2, 3 and find out the direction. If it is clockwise, we call them R, and if it is anti-clockwise, it is S, right? So let's take this molecule and do it, right? Now, this is the molecule. You have iodine, bromine, and chlorine. So according to the molecular weights, molecular atomic number, you give number 1 to this one, then comes the bromine and chlorine last, and not the last, third one, and higher, the lowest weight is, the atomic number is hydrogen, right? And it is getting number 4, right? Now that is not enough. Now the lowest one is hydrogen, lowest priority is hydrogen. The molecule is not having the least priority group away from you. According to this structure, we have iodine away from you, which you have to, which is having the highest priority. So you have to change. So on paper, it is difficult to change that. Now, if you have a model, the stick and ball bottle with you in your hand, you can do that. But on paper, how to do it? There's a way of doing it. What you do is interchange. Now, this is to get the hydrogen away from you. So actually, we need to get hydrogen to this position, which we have to change, remove iodine and put hydrogen there. So interchange 2 groups once, right? So what we do is we are going to change these 2 groups. And now when you do that, configuration of the molecule is changed, right? It will happen because we have changed the groups. Now you have iodine here and hydrogen here. So when you read the numbers, priority order, it becomes 1. These 2 are pointing towards you. So imagine this is on the plane of the paper. This is pointed towards you, and this is also pointed towards you. So when you turn, it is R, the S, right? It is anti-clockwise and S, right? This is S configuration. But now what we have done is, we have done only one interchange and change the configuration of the original molecule. So after changing, it is S, but the original molecule should have R because we got S after changing these 2, right? So if you do 2 interchanges, similar way, this is 1, you do another change, you get the configuration of the original molecule. Remember, if you do 2 interchanges, you are going to get the original molecule configuration. So if you are doing only 1 interchange, remember the configuration you are getting is for that changed molecule, and the original should be having the other configuration. But if you have done 2 interchanges, you don't have to worry. You are getting the configuration of the original molecule, right? So see, now we are going to change these 2. Originally, we changed this one. You can do any. You can select any 2 groups. Now I'm going to take this one and this one. You can either take Cl and Br1, right? But I have selected. Now first interchange is this one. You get hydrogen here, iodine here, and the second interchange I'm going to do with iodine and bromine. So I will get a molecule like this. Bromine on top, iodine here. Hydrogen we are not going to move because the lowest priority group should be away from you, right? So as I said, with 2 interchanges, you get the molecules identical. You get a molecule identical to the original molecule. Here you can't see because when you compare the groups on these structures, it is different, but the configuration is the same. Remember, when you do 2 interchanges, configuration, whether it is R or S, is going to be the same with 2 interchanges. and you get the original configuration in this model. Right? Remember, it is after 2 interchanges. Right? Now, try to read the numbers. You get 1. I did 1 here. 1, 2, 3. And it is going to be R. Clockwise is R. Right? Now, when you do 1 interchange, we got S. And we said it is original should be R. Now here, after 2 interchanges, it is R. And the original also should be R. Right? So clockwise rotation, R configuration. Right? It's very easy. Only things you have to remember, only the things you have to remember is all the time you have to keep the molecule so that the lowest priority group is away from you. Right? So you have to have an arrangement like this or this. So the other thing you have to remember is if it is rotating anti-clockwise, it is S configuration. If it is clockwise, it is R configuration. And the other thing you have to remember is if you do 1 interchange, you get the opposite configuration. And if you do 2 interchanges, you get the original molecule and the original configuration. Right? So if you know these things, you are not going to make any anything not going to go wrong in naming the configurations of the asymmetric carbon atoms. Right? Okay, so hope you have understood, right? So if you don't understand, again, go through this material and try to understand. Now, again, exercise. Fisher projection formula for molecule is given below. Now, you know, this is Fisher projection. You have to be very familiar with Fisher projections, Newman projection. I have shown Newman projections for this ethane and butane. And then those are the projections where you had this carbon with indicated with a circle and the other bonds with lines. These are Newman projections, and there's another way of representing molecules within this, which is called Sawhorse projections, right? So all 3 types you have to know, and you should be able to draw the structures of molecules using these projection formulas: Fisher, Newman, and Sawhorse, right? So Fisher projection formula for molecule is given here. What is the configuration of the chiral carbon atom in it? Now you have to find out what the chiral carbon. You can straight away say that there's a chiral carbon atom because this carbon atom has all 4 different groups attached to it, right? So asymmetric center is there, stereo center is there, so it is a chiral molecule. So you have to find out the configuration, whether it is R or S, right? So how to do it when you have a structure drawn like this, a Fisher projection formula, right? Now we have to know how to convert it into a 3-dimensional structure, right? When you have a Fisher projection formula, it is all on the paper with lines like this, right? So when you are showing the 3-dimensional representation on paper, you can draw the center of carbon atom like this, and all these horizontal lines are drawn like this. They are projecting towards you, and the vertical lines, cirrus iri, vertical lines are going away from you, right? So when you represent this as a 3D molecule on paper, you have to draw like this. Remember, these lines, horizontal lines, are projecting towards you, and the straight the vertical lines are away from you. So this is the 3D representation of this Fisher projection, right? Now, when you have it like this also, it is difficult to find out the configuration. If you have some bonds on the plane of the paper only, it is easy for us to find out the configuration, and we can arrange them we can arrange the molecule by tilting the molecule to get one bond on the plane of the paper. So you can do something like this. You can turn the wand and get this CHO group on the plane of the paper. So when you do that, this CH3 again, still it is away from you, and this hydrogen and OH also still pointing towards you, right? You just tilt a little so that the CH3 CHO group is on the plane of the paper, right? And then you have the required way of drawing here, right? What we need is this type of a molecule. So see, we had this here. Originally, the Fisher projection is like this. So when you draw it, you get a structure like this. Now it is easy for us to number the groups according to the Carnegie-Gold-Prelog rules, priority order. So you have oxygen, carbon, carbon, and hydrogen. So out of carbon and oxygen, oxygen gets number 1, and then this group gets number 1. And out of carbon and carbon, CH3 here and CHO, where OH oxygen is attached, is getting the next priority, right? And the third priority, according to the priority order, this is 3, and hydrogen gets the lowest priority. Now, this is again not suitable for our nomenclature. We have to put hydrogen away from us. Now, according to this one, CH3 is away. You either do one interchange and get the opposite configuration, or you do 2 interchanges and get the original configuration. So let's see, when you do one interchange, what are those? So I have here, I have changed. Anyway, we have to get hydrogen here. So it is easy to do the interchange with hydrogen and CH2. So you get something like this. So the way of rotating is 1, 2, 3. It is S, right? So this is S. So remember, if this is S after one interchange, this is going to be R, because with one interchange, you get the opposite configuration. So original molecule is R. So let's see when you do 2 interchanges, right? So you do an interchange 1, same like this one, earlier one, and the second one, you get, what are the groups I have changed? CHO and OH. Don't change hydrogen again, change whatever, any 2 out of the other 3, right? So in this case, I have changed OH and CHO. And see now, according to the order, 1, 2, and C, this one. This is towards you on the paper, away from you, right? 1, 2, 3. So it is clockwise. Clockwise means R, right? So this is as same as the original one, right? So that is how you find out the configuration of asymmetric carbon atom or a asymmetric molecule or a stereo center of a tetrahedron geometry, right? So hope you have understand, and it is very clear. Now I have taught you how to do it. Now you don't have to worry about imagining the 3-dimensional structure in space, right? If you're having the molecule on the plane of the paper, when you do now, it is, you can see it is very easy. Only thing you have to remember is if you do one interchange, opposite structure. If you do 2 interchanges, you get the original configuration, right? So I have made it very easy for you to identify the configuration of a stereo center now. Now, when we were studying, nobody explained it this way. So on our own, we tried to understand, and it's a very harder way that we understood. Nobody explained it to me the way I have explained to you, right? In the books also, I don't think that you get. But in our book, course material, it's very simple. And don't try to imagine the 3-dimensional structure. So you don't have to have models in front of you to find out the configuration, right? Okay, so only thing is you have to convert the Fisher projection formulas into 3D structures. So give the configuration, second exercise, give the configurations of the stereo centers of the compound given here. First of all, see whether there are stereo centers. So you have one carbon atom, not a stereo center. This carbon atom, again, not a stereo center. This carbon atom, 4 different groups, the stereo center. And this carbon atom, 4 different groups, the stereo center. And this carbon atom is not a stereo center. So overall, this molecule has 2 stereo centers, right? So give the configurations of the stereo centers. So for both carbon atoms, you have to give the configurations, right? So as I said, you have to get it changed to this Fisher projection formula should be changed to a 3D structure. When you do it on paper, you can do like this. The vertical lines going below the paper. So CH3 goes below the paper, CH2, CH3 goes below the paper. And horizontal lines point like this, pointing towards you. Both hydrogens and chlorines pointing towards you. Still, now it is easy for you. I have put it as homework. Now it is easy for you. You break the molecule into 2 halves and get this as a whole group, one large group. And when you are considering this carbon atom, this is one group, hydrogen, chlorine, and this one. And when you are considering this carbon atom, take this as a large group, chlorine, this one and this one, right? So separately, you do the changes. And as I mentioned earlier, what you have to do is, if you are considering this one, you have to change the hydrogen, put hydrogen away from you. So first thing you do is you change this one and this one. So the hydrogen is away from you. So if you want to do one interchange, you can do it and get the configuration as the opposite one. If you want to do 2 interchanges, you do this one, and now hydrogen is here. CH2, this big group is here, and chlorine is here. You can change these 2. This big part is difficult to change, so that we can change these 2. Still, hydrogen is away from it. So find out the configuration. First, get the priority order and find out whether it is clockwise or anti-clockwise. So it's for your homework. So if you want, you can take the structures down. I will give you 1 minute to take down the structures. Now find out whether this carbon atom is R or S and this carbon atom R or S, whether it is R or S. Okay, let's move on. Another question from one of the past papers. Determine the configuration of the stereo centers of the following compounds. Compound B. B is not there, but this is the compound. Right? Carbon atoms are numbered for your convenience. There's no order. Now, when you are naming the compounds according to IUPAC nomenclature, you have to number the carbon atoms a systematic way. There's a way to number. But here the numbering is done for your convenience only, not according to this IUPAC, UPAC, right? Just a way of numbering for identification, right? So what you asked to do, determine the configurations of the stereo centers of the following compound. First of all, find out how many stereo centers are there. Or else you have to identify the stereo centers. Identify what the stereo centers are, right? And then you have to find out if you have a double bonded system, whether it is E or Z, or if you have a tetrahedron stereo center, whether it is R or S, right? So first of all, try to identify the stereo centers. You do it. Go along the carbon skeleton one by one carbon at a time, and check whether asymmetric carbon is there. And if you have a double bond, find out whether 4 different groups are attached to the double bond. When you are putting answers in the chat box, put it only for me, not for everyone, right? So if you put it for everyone, they know the answer. Now you have given correct answers for those questions before I explain. Good. That means you have understood what I have explained, and you have a genuine, if you have made a genuine effort to understand the thing, even without reading the book. Some of you have given direct answers to me only. Good. Okay. Let's see. Now, first thing is to identify the things. Now you have this molecule, the stereo. Now when you go along the carbon skeleton, this carbon is not a stereo center. This carbon is a double bonded carbon. You have a double bond here, and all four groups are different. CH2OH, hydrogen, CH3 and this group. So it is going to be a trigonal planar stereo center. One is there. And this carbon atom, again the double bonder, and this carbon atom. So when it is not, when the groups are not shown, that means hydrogens are there. So carbon number 4 has 2 hydrogens, not a stereo set. Then C5, nitrogen, this carbon with OH, and this big group, and which is not mentioned is a hydrogen. So it is a carbon with 4 different groups, asymmetric carbon or a stereo center. And 6, carbon 6, OH group, this part, and again the other one is big, this one, this part, and a hydrogen, right? And again 4 different groups, asymmetric carbon atom and a trigonal planar stereo centers. And 7, 8, and 9 all are having hydrogens, 2 hydrogens. They are not stereo centers. And this one, 1, 2, 3 atoms only. No 4 groups here, right? So nitrogen 3 valency is 3. We don't consider, right? So this molecule has 1 stereo center here, another one at C5, and another one at C6, right? So how to determine this one? Now I have to make the things easy. I'm putting the answer here. Now you know how to give the priority, label the groups according to the priority order. Consider this one and this one. Out of carbon and hydrogen, this gets the high priority. So number 1 is this, 2 is this. And when you consider this one, this large part gets number 1, and this is 2. So it is 2E, right? This I have put 2 according to the way it is numbered, right? Not according to IUPAC, right? Here we'll take the 5th carbon atom. You have this nitrogen. Now when you are labeling, numbering the groups, nitrogen has priority over carbons, so it is number 1. And out of these 2, you have C4, another C, like that. But in this case, you have a carbon and an oxygen. So you go along the skeleton until you get a difference, right? So when you consider this one carbon and another carbon, this one carbon and oxygen here. So this is number 2. And this one, number 3, and hydrogen is luckily, it is away from you, right? Now, when you have this one as a solid line, that will automatically we get the idea that the other one is, this is pointing towards you, and the other one is pointing away from you, and hydrogen is away from you. So you don't have to rearrange anything. We have it in the order we want, the way we want. So it rotates 1, 2, 3 like this. So it is clockwise and R. And this one, carbon 6, you have hydroxyl, this whole part, and this whole part, and another skeleton. So all when you consider this carbon atom, the next is oxygen here, the next is carbon here, the next is carbon. So this gets number 1. So out of these 2, you have carbon and then nitrogen. Here, carbon and carbon. So nitrogen, when you have nitrogen, this gets the priority, right? So this is number 2, and hydrogen is number 4, right? So if you want, I have not shown the way we have done the changing the groups to get the correct order. But you know, when you change these 2, you get hydrogen away from you. So OH comes here. When OH is here, you get number 1, 2 like this, and it is R, right? But that is, you get R after changing once, one interchange. So if it is R, the original should be S. So you can put it as R6S. Understood? I think it's clear to you now, right? So if with this OH away from you, it is difficult to determine the configuration. You have to get it here and put hydrogen away, right? Okay, so I think it's clear to you now. Let's see quickly what other important things are. Now, we were talking about enantiomers, diastereomers, mesoisomers, and a lot of words, new words came, right? So you have to know all the meanings of these words when you are learning stereochemistry. So let's see what epimers are. Now, epimers are diastereomers which differ from configuration in one stereocenter, right? And the epimeric, when you are labeling or naming them, epimeric position should be specified. So without going to the definition, let's see what is happening there. Now you have this D-glucose. This is the structure of D-glucose. And if you have a different arrangement in this carbon atom, now in D-glucose, you have OH here, and in D-galactose, you have OH to the other side. But all the other attachments are the same. This carbon atom, OH the same, OH is here, and this one, OH is here, OH the same, similar. All the other arrangements are similar except for this OH. So we call this galactose is a epimer of D-glucose. And as I mentioned, as it is mentioned here, epimeric position should be specified. So we call it C4 epimers, because when you in a molecule like this, you have to start numbering from this end. This aldehyde position, aldehyde carbon, 1, 2, 3, and 4 position. The difference is shown at 4th position, and we call it, it's a C4 epimer. And remember, all the other stereochemistry of all the other carbons are similar here, except for this one, right? It's a C4. So likewise, you can have this structure, the glucose structure, and you can have different epimers like C3 epimers. In a C3 epimer, same as this one, the only difference is that this carbon atom should be the other way, right? Like that here. And it is not going to be the galactose now when you have a C3 epimer, some other name, right? Okay. So conformational enantiomorphism is a very complicated thing, but if you try to understand is you pay your attention fully, you will understand in the first instance. Now, I'm going to show it to you. Try to understand. Now, the presence of a chiral conformation as a pair of enantiomers in a equilibrium. The definition for conformational enantiomorphism is two enantiomers in equilibrium, right? So let's take this example. This is tartaric acid. This structure is the structure of tartaric acid. You can see I have put a dotted line here, broken line here to show that it is a meso compound. It has two similar parts, symmetry. Their axis of symmetry is there, right? So that it is called mesotartaric acid, right? So now you know how to convert these Fisher projection into 3D structures. So we keep this straight line here and put the vertical lines away from you and the horizontal line towards you. So this is the 3D representation. This is the sawhorse representation of the same molecule, right? So when you put it into this sawhorse structure, this CO2H group, carboxyl group has to go down, and this also has to go down below this one, right? And all these are above the if you when you put carbon dioxide below, others should be above, right? So try to understand how to convert a Fisher projection into this 3D and how to convert that into a sawhorse projection, right? If you don't put it in the correct way, your the configurations are going to be wrong. So if you have put CO2H by mistake up here, it's going to be a different configuration, right? So now what I'm going to show you here is a different phenomena, but remember you should learn how to represent them, and what I have mentioned, not mentioned here, is Newman projection formula. Okay, so right, so we'll take this one, the carbon dioxide molecule, and here this one after the drawing the projection, we can now, I have mentioned that carbon single bond can rotate. So when you rotate, you can get carbon dioxide here, carboxyl group here, OH here. Now rotate this at a 60-degree angle and you get this structure. Now this conformation, you call these conformations, is a chiral conformation, not symmetry, right? But here you have a symmetry and this one is symmetry. But when you have this conformation, when you rotate this along this axis, you get a chiral conformation. You call these conformations, right? And another turning is done to get the carboxyl group on top, and you get a symmetric array. Now you have along this center, it has a center of symmetry, right? You have these groups, and the three groups on this one along this center is similar, right? Center of symmetry is there, and it is going to be when you have a center of symmetry or center of plane or axis of symmetry, they are going to be achiral, not chiral. And again, you can have another structure. Now I'm rotating the groups of this carbon only, right? You get the arrangement like this, right? And it is again going to be a chiral, no center of symmetry or axis of symmetry or line of symmetry, right? Now consider this chiral atom, chiral molecule, chiral conformation, you call it a conformation, and look at the molecule from the other end. Now when you look at this molecule from this end, you have this OH to your right hand side, hydrogen onto your left hand side, right? Now in a solution, you can't observe the molecules like this. They are turning any direction, right? So in this molecule can be observed from the other side also, right? So if you draw the appearance from by observing, viewing it from the other side, rear end, right? I have put an I here. So when you weave it from the rear end, you get the CO2H on your right hand side. So I have put here, and OH on your left hand side, and hydrogen on top, and the other things same way, CO2H below downwards, and OH on your left hand side and hydrogen on your right hand side, right? And now this molecule, as I said, these molecules can rotate on their carbon-carbon single bond. So when you rotate, you get this arrangement. You get this one, you rotate this and get OH here, CO2H goes down, hydrogen here, right? And you get this molecule. Right. This is again C. All these are C because of the screen. I can't see below this one. Right. I have put a C here. Maybe you can see them, right? So the same C molecule, same chiral molecule is here and here. This is from the other side, weaving from the other side. And this is after a rotation along the carbon-carbon axis. Now you can see this C, my C, the last molecule labeled as C is the mirror image of this A. Right? This is A molecule, this one, and this last, this C is the last C, weaving from the other side, right? And you can see these two are mirror images. These two are mirror images. So originally we couldn't see it. When you draw the molecules like this one and this one, we can't see as mirror images. But actually the molecule, because of this the symmetry, it is going to be like this when you weave it from the other side, and A and C are mirror images. When you have them like this, you never can say that they are mirror images, right? And this is called the presence of chiral conformations as a pair of enantiomers in equilibrium. Now in a solution, these two will be in equilibrium, right? So one is converting to the other and the other one is getting converted to the other. So that is called conformational enantiomorphism. So this is, I have taken this example, a linear molecule. So in cyclic molecules also, you can see this, right? Okay. So we are coming to the end of coming towards the end of this thing. Let's discuss about chiral molecules and optical activity, right? Now, chiral molecules are called optically active molecules, right? Because these chiral molecules, that is molecules with asymmetric center, can interact with plane polarized light. What is plane polarized light? You know, this normal light is unpolarized, right? So because the waves vibrate now, according to this picture, you can say in unpolarized light, waves vibrate in all directions, right? So there are special filters. When you pass this unpolarized light through the filters, you can get polarized light, where the vibrations are only to one direction, right? So when you pass this polarized light through a chiral molecule, we keep a glass or the beaker of beaker with a compound with chiral molecules, right? So what happens is one conformation will rotate it, change the direction of the polarized to one side, and the other compound, the other configuration will change the direction to the opposite side. So we call them plus and minus, right? Enantiomers, actually enantiomers. Now in a chiral, if you have a mixture of chiral molecules of a compound, that is enantiomers of a same compound. So one enantiomer will change it to one direction and the other enantiomer will change it to the opposite direction, right? So that is why it said enantiomers rotate the plane of the plane polarized light in opposite direction. And remember, there is no relationship between the configuration and the direction of rotation, right? Now, you can't say our configuration is going to change the direction to plus side, or whether its configuration is going to rotate it to the plus side. So there's no relationship, but they will, the one enantiomer will change to one direction, and the other enantiomer will rotate it to the opposite direction at the same angle, right? So you read more to get more clearer idea, right? So let's do this exercise to understand what compounds are optically active or not. Now, we were discussing that when a chiral center is there, these compounds can be optically active, but if the molecule as a whole is not chiral, remember molecule, not the carbon atom. If the molecule, that molecule can have several stereo centers or asymmetric centers, but as a whole, molecule is having a center of symmetry or axis of symmetry or angle, whatever the way of symmetry is there. So that is not going to be optically active, right? So we'll take this compound. You have several carbons, carbon here, carbon here, carbon, carbon, carbon. Only this carbon is having a stereo center, the asymmetric carbon. Okay, this carbon is asymmetric, right? Others are not, right? So this can have this is having 4 different groups, and this is going to be a chiral molecule. The molecule as a whole is a chiral molecule, so that it is going to be optically active. And take this compound. Now this compound, actually there's no asymmetric carbon also, and also it has a center of the axis of symmetry, so that actually it is a plane of symmetry. Along this plane, it is similar, so that it is not optically active. So it is optically inactive. Take this compound. You have carbon and carbon, OH and OH, right? So does it have a plane of symmetry or a center of symmetry or a axis of symmetry? Along this axis, it's not symmetric. If you get it, cut it along this one again, you don't have any of this one, right? So no symmetry there. It is optically active. Now this compound, it's tricky. Now, as I have explained in when you are drawing the chair conformations, you can put this BR to any position here, any position of the chair. Only thing is, you have to place the other carbon at the right position. When you put BR here, so it has to be 1, 2, 3, third carbon. So you put no 1, 2, 3, fourth carbon, right? So you can have BR or this BR here to this carbon. Since it is below the plane of the paper, it should be like this, equatorial. So the fourth carbon atom, the other bromine is there, and it is projecting upwards, and these two have to be opposite. So if it is below, this is to be above the paper, right? So here you can see when you have a plane, when you cut the molecule, is imagine the 3-dimensional 3D structure of this molecule. If you cut the molecule along this axis, where half of the bromine atom is cutting and the other half of the bromine atom is also cut, right? And bromine atoms are cut into half, and you have 1/2 of the molecule here, 1/2 of the molecule here, so that this molecule has a symmetry. When you look at this one, you can't say. When you look at this structure, you can't, difficult to say, right? So you have to convert it into this form, right? So it is having a plane of symmetry, so that it is optically inactive. So when you get a structure like this, draw the other arrangement like this and see whether it is symmetrical. It's having any kind of symmetry. This one, at the first glance, you can't see anything. Flip it. Flipping means, now you heard the word flipping in my videos. That is, change the position of this one. If the top is top part is going to flip into the bottom downwards, and this part going to flip into the top, right? So that happens here, and when that is happening, you get, now it has to, this methyl group should be above the plane of the paper, above the imaginary line. So it will become above, but axial position will become the equatorial. So this one axial, but it becomes this is equatorial, it becomes axial when flipping happens, right? And again, same way, you can change the positions. You can turn the molecules, because the molecule we are drawing like this can be turned to any direction. You can turn this molecule to any direction. Anyway, if you have a model, you can do that and see. So when you turn, you get this array, right? Methyl up, and the next methyl equatorial like this. And you can see these two molecules are mirror images, enantiomers, right? And if you have this compound in a vessel, beaker, right? Cyclohexane with these two methyls like this stereochemistry, it will have these two enantiomers in the mixture. So that these are enantiomers, and enantiomers are inactive. Enantiomer mixture are optically inactive. So enantiomer mixture, if they are having in equal amounts, one molecule, one enantiomer is rotating to one side, and the other enantiomer is rotating the same same light wave to the other direction from the same amount, so that you can't see any rotation, because if you have the equal mixture, rotations cancels off, right? So racemic mixture, this is going to be a racemic mixture, so that it is optically inactive, right? So when just by looking at the structure, sometimes in the cases like this, you can't say whether it is optically active or not, but you have to draw the other possibilities of having this arrangement of these molecules and see whether they are optically active or not, right? So the next thing you have to learn is optical activity, and we calculate percentage activity of mixtures, and it's also called percentage optical purity. So this is the equation we use to calculate optical purity. So when you are measuring the optical rotation, you calculate it by this angle alpha d, alpha, like you denote it like this. So it is going to be plus this angle or minus this angle. And we know we have reported values for pure isomers. If you have a compound, say maybe this one of these phthalimide, say phthalimide pure isomer will have a certain angle of rotation, and we know it is reported, right? And if you have a mixture with R and S thalidomide, right? Sorry, thalidomide, R and S thalidomide mixture, and we measure the optical angle rotation to the mixture and find out the value, right? And we can find out the percentage purity, optical purity of that mixture by putting the values into this equation, right? So the pure value we know, mixture value we can measure and calculate the optical purity. So there's another calculation which you have to be familiar with, that is to calculate the enantiomeric excess. Enantiomeric excess is calculated according to this equation. That is the moles of one enantiomer. Imagine you have a mixture of enantiomers, right? Maybe one enantiomer is more and the other one is less, right? And you can calculate the excess, which enantiomer is more, by this equation, by finding out the moles of one enantiomer and deduct the number of moles of the other enantiomer and divided by the total number of moles of the both enantiomers and multiply it by 100. And it is shown when you read the book, you can see the enantiomeric excess denoted by E is equal to percentage of optical purity. This is what we measure practically. We can measure this practically by using a gadget, right? Polarimeter. And this one you can calculate. So for that, you have to know the number of moles. But when you don't know the number of moles and all, you can find out the enantiomeric excess by finding out the optical purity. For that, you have to measure the angle of rotation of the mixture, and you have to know the angle of rotation of the PO isomer, right? So this is an exercise again from one of the past final exam papers. I'll just explain it, right? So because without going deep, you will not understand. Just give you the summary of what is asked is for a optically pure this compound pseudoephedrine. It's a drug. Pure plus pseudoephedrine is plus 52. Rotation is this much for the pure compound. Alpha D of a synthetically prepared sample. So somebody has prepared a sample of this one, and it was found to be this one, right? And calculate the enantiomeric excess and the percentage of plus pseudoephedrine in that synthetic sample. So that what you get, the idea you are getting is the synthetically prepared one is not only plus pseudoephedrine, might contain minus this one. That is why you're getting a less rotation here. If you had only pure ephedrine, angle should be this one. So how to calculate enantiomeric excess and the percentage of pseudoephedrine in that synthetic sample, right? So we calculate the enantiomeric excess by using that equation, the former one, you know, the alpha D of the sample. This is the alpha D of the sample, synthetically prepared sample. This is the alpha D of the pure sample, which is given here. And you multiply it by 100 and you get 78% here. What does that mean? Now, if you have a sample, now this is the synthetic sample, right? Enantiomeric excess is 78%. Now we are interested in plus isomer, right? The chemist had tried to synthesize plus isomer. So the excess of that plus isomer is 78. So what is the rest? Excess is this much. The rest, the balance, 22%. 100 minus 78 is 22. So the balance is the racemic mixture. You have plus isomer half and minus isomer the other half. Balance of this one is 22. 11% is plus isomer and 11% is minus isomer. So now with this minus isomer, same amount is going to cancel off like. So this is the racemic mixture. 22% is the racemic mixture. You have you have 78% excess in excess of the plus sample. This is actually this. If you have to know these equations only, and the rest of the calculation or the problem is like this grade 5 scholarship questions, right? So you have identified 78, and this is 78, and the rest is 22, and you have to consider half as the racemic mixture, right? So what is written here is what I have just explained, right? So the other type of questions, actually, I have been targeting the final exam questions here, how to answer. Now, the latter part of the thing, I have put these things because there's nothing much to discuss about these things. You have to know how it is done. How would you attempt to separate a racemic mixture of lactic acid into optically pure plus and minus lactic acid? So the lactic acid structure is there. Actually, the experiment is explained there, not for lactic acid, something else, I think. But what you do is, I have shown it in a two-way key like this. You have the mixture here. That mixture means, now you know it's the racemic mixture because plus and minus, these things are there. So plus and minus maybe R, it is actually RNS. We can't say that R is plus or R is minus. It can be R, this plus is, can be the plus maybe R, or sometimes plus maybe S. So for a different compound, R can be a minus compound, right? So there's no relationship between this plus and minus and RS configurations. In this, I have mentioned that also. So maybe one configuration is rotating towards the positive side and the other one is to the other direction, right? So you have this racemic mixture and you know it is an acid. You react with the pure base, right? So pure base means it has to be maybe a R base or it has to be a S base. You have to select one type, right? Not R and S mixture, right? So say you have taken R base. The configuration of the base is R, right? So when you know acids react with bases to give you salt and water, right? So this base reacts with lactic acid. This is the acid, and since you have the mixture here, racemic mixture here, R and S both here, you get the RR salt and SR salt both, right? And these salts are, because of these different configurations, they have these different physical properties. Maybe the crystal shape is different. Maybe there is RR salt is having a lower boiling point and this one having a higher boiling point, or maybe having this is a arch crystal with the hexagon, the shape is different shape than the other one. Like that, they have different physical properties. Maybe this is maybe since they are for salts, they are water soluble, that cannot be considered, but they are having different physical properties. So, so you can at this point you can separate out the two salts. If it is crystal shape, you can manually pick up, or there are ways of separating out the crystals. Or maybe you can see if there are some crystals are larger and the other one is smaller, you can have a way of separating out. And then you hydrolyze them separately. When you hydrolyze the salt, you get the acid and base separated. And when you hydrolyze RR salt, you get the RR acid, R acid. And when you hydrolyze the RS salt, you get the SS. So you can, this way, you can separate out the RNS lactic acid mixture. Right now, these are applicable in drug synthesis and drug, mostly in drug industry, because you know the gravity of not knowing the stereochemistry of the drug thalidomide, right? So these applications are mostly in this drug synthesis and development, right? So this part is also there. So there are several things which I have not discussed at the D school. That doesn't mean that you are not going to be tested on those. As I have mentioned at the very beginning, this is going to be a guideline, the foundation for your studies, because most of you have seen that have not studied the book fully, right? So we'll end up with the poll. I